Hey guys, this is Carrie, and this is going to be our last lesson in the trig unit. We did like two halves, first half, second half. We're going to do a final review of everything we've learned this unit, and then we're going to do a final test on Delta Math on Thursday for our next class. All right, so here we go. Let f of x equal 4 sine 6x minus 2. Determine the maximum value, minimum value, and period of f of x. So at first, this question might be scary. This is a problem that we've never answered before regarding maximum and minimum values. But on second thought, we know how to graph sine cosine functions pretty well. So let's graph this guy and see if we can pick out the important details. So here we go. All right. Going to have a vertical shift of minus 2. Amplitude is 4. So you go 1, 2, 3, 4 up to make 2. That makes sense. Negative 2 plus 4 is 2. And then we're going to go 4 down. 1, 2, 3, 4. 4 down is negative 6. So plotting in our midline, there we go. Now we know as well, sine is going to start here on the midline. But before we can graph sine, we need to figure out the period of this function. So to find the period, we say, okay, well the period is when the inside of our sine function, when this hits 2 pi, that will be when it completes a full cycle. So to figure that out, we divide by 6 on both sides, and we see that x is equal to pi over 3 when you reduce the 2 and the 6 to give you pi over 3. So one period is going to be pi over 3, which is right here. All right, now we also need the halfway mark, we'll need the quarter way mark, and we'll need the 3/4 way mark. You can find the values for these, it's not too bad. Halfway in between pi over 3 and 0 is pi over 6, because you divide this by 2, making it over 6. Halfway in between that is pi over 12, because you do pi over 6 divided by 2, giving you pi over 12. And that would make this 1, 2, 3 pi over 12. All right, but even if you didn't figure that out, you could still graph this function totally fine. So here we go. It's a sine function, regular amplitude. So we go up to our maximum value, down to our midline, down to our minimum value, back to our midline. And there we go. All right, maximum value, where we hit the top, 2. Minimum value, the bottom, negative 6. Period is pi over 3. All right, so graphs are super helpful. And last time we looked at using graphs to come up with application type problems. So here we go. The equation below is used to model the volume of blood, V of t, in someone's heart, measured in milliliters as a function of time t, measured in seconds. Well, this actually makes a lot of sense. If we think about the amount of blood in somebody's heart, it's gonna, sometimes it's going to be more, sometimes it's going to be less, depending on whether that heart is compressed or whether it's filled with blood, because a heartbeat, right, compressed and filled with blood. All right, so sine functions seem like the right tool here. Up, down, up, down. Looks like cosine actually, but we just use the term sine function to represent either sine or cosine. Of course, ours will not look like this because it's cosine. It will look more like this. All right, but let's get the details. So here we go. We need to scale our axes appropriately. If we're going to do a vertical shift of 75, we don't want to count 75 boxes up. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've only got 10 boxes to work with. And we want to go up to 75. So I'm going to do a bit of thought here before we graph anything. If 75 is going to be the midline, the vertical shift, and the amplitude is, go away thing. The amplitude is 23. Then the maximum value that we're going to hit is 75 plus 23. That's going to be 97. And the minimum value that we'll need to hit will be 75 going down the 23 from the amplitude. That's going to be 52. All right, so 52. So between 97 and 52. With 10 tick marks, I think the best choice is to go up by 10s. So we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And you can see we're going to have 97 and 52 on this spectrum. So let's mark them, 52, 97. All right, I'm going to graph in the midline at 75. 1, 2, okay, right between 70 and 80. So there's our midline. 23 is the amplitude, so we start off because it's cosine, but before we graph it, we've got to figure out the period. So to find the period, we set the inside equal to 2 pi. We divide by 2 pi on both sides, and that tells us that the t value is 1. So this heart is beating once per second because it goes through a full cycle. Full of blood, empty with blood, back to full of blood. And when you say empty, it's not actually empty of blood, it's just down to its minimum amount of blood after it compresses. And then it's back to its starting value right here. This is 1 second because that's how long it takes, according to our calculations, to make one full cycle. All right, we're supposed to graph it over this domain. So I don't know. Let's see. 1, 2, 3, 4. Let's make this 1. 1, 2, 3, 4. Let's make this 2. So this will be 1 period because of this calculation, and this will be the second period here. And we will, if we stop at this line 2, we will have done the appropriate domain here. They gave us a bit of extra space, but that's okay. All right, so here we go. Let's graph it. All right, we start at the maximum value. Oh, I don't want to use green because I used that already. We start at the maximum value. Here we come down to the midline. Here we come down, this is on the halfway mark. We come down to the minimum, just like we have up here at the minimum. Here we go back to the midline at the 3/4 way mark, and then we go back up to the maximum at the full period. But we're supposed to graph it on this domain, so we need to do it one more time. Midline, minimum, midline, maximum. And we've got our graph perfect. So this is a heartbeat. All right, so to determine the period of P, it's not period of P, the period of V of T. I don't know why it says that. Explain what the value represents in the given context. So we found that the period is T equals 1, and the units of T, they told us, were seconds. This is the amount of time, by definition of the period of a trig function, this is the amount of time it takes to repeat one cycle. But we want to be more specific, right? Because they gave us a context. What does a cycle mean in the context of the volume of blood in someone's heart? It means how long does it take to have a heartbeat? This is the amount of time to complete one heartbeat. Sick. All right, continuing on. Wow, so going way back, way back. Before we talked about waves, before we talked about circles in the coordinate plane, trig started off about triangles. That's where the tri in trig comes from. And then we built from there up. So let's start over again, because this is a review lesson. All right, in the diagram below of triangle BYH, angle Y is a right angle, got it. Using the information in the diagram, determine the measure of theta. So this is our fancy Greek letter that we use instead of x. It's like x, right? All right, so we need to find theta. So we'll label our sides. We've got the side that's opposite theta. Here's the adjacent. And then across from the right angle is the hypotenuse. So we're going to look for one with the opposite and the hypotenuse. All right, because we're working with the right triangle, we go so, ka, toa. Opposite hypotenuse, that's sine, so we set it up. Sine of theta is equal to 14.9, opposite, divided by the hypotenuse, 16.7. All right, last step to solve for sine here, we need something that will get, sorry, I said that wrong. The last step to solve for theta here, we need something that will get rid of sine. And we learned very early on, the opposite of sining something is to do sine inverse. So sine inverse will cancel out with sine. But if we do sine inverse to this side, we've got to do sine inverse to this side as well. That gives us our final expression to plug into the calculator, sine inverse, 14.9 divided by 16.7. Now, really key here, we did not emphasize this, but round your answer to the nearest degree. So make sure you're in degree mode, because we learned that there's another way of calculating these things called radians. So we go to Desmos. We change it from radians to degrees. We find our functions. Wow, this is like our whole unit right here. Sine inverse 14.9, I think, divided by 16.7. Let's see if we got that right. All right, so 14.9, 16.7 is what I think it is. Yeah, hey, we got it right. All right, so let's look at the answer. 63.15. But if we leave it like this, we just lost a point because they said nearest degrees, so that should be a whole number, 63 degrees. Awesome. An angle with measure 880 degrees, whoa, is graphed in the coordinate plane. In which quadrant is its terminal side? All right. So we learned that sometimes angles are too big to fit in right triangles, so we graph them in the coordinate plane. We start off with the beginning of the angle, the starting side, on the positive x-axis, and then we rotate counterclockwise from here. So if we got to here, that would be 90, this would be 180, this would be another 90, 180 plus 90 is, okay, 270, so this is 270. Completing a full circle is 360, but we want to graph 888 degrees. So we're going to do at least one full circle. That's 360. We do a little bit of subtraction here. 880 minus that full circle leaves us with 528. We got enough for another full circle, actually. So we go another full circle. We subtract off that 360. That leaves us with 168. So we've done two full circles and an extra 168 degrees. So our terminal side will be here in the 1, 2, 3, 4 second quadrant. All right, here we go. I'm not sure if we talked about the vocabulary in this one, but it's a helpful piece of vocabulary to know. So an angle of measure negative 125 degrees is graphed in the coordinate plane. Which of the following angles is coterminal with this angle? All right, negative 125 degrees means that we're going to be going starting from the positive x-axis. Let me use a different color. Sorry, let me use a different color. Okay, different color. Starting from the positive x-axis, we're going to go opposite direction because it's negative. So this will be negative 90 degrees, negative 180 degrees, negative 270 degrees. And then if we got all the way around, it would be negative 360 in this case. Negative 125 is going to be here. Halfway, not halfway, somewhere in between negative 90 and negative 180. All right, so what does coterminal mean? Coterminal means it ends, because you see the word terminal, that means it's ending. Co means with in general, but in this case it ends in the same place. So we're looking for an angle out of these ones that ends in the same place. All right, so let's test 35 degrees. If we started here and we graph 35 degrees, that's super tiny. That is not sharing the same terminal side. Wow, I keep doing that when I mean to press undo, sorry. All right, so 35 is out. 55 is too tiny. It's also in the first quadrant. 125, that's going to be here. That's not ending in the same place. But if we do 235, let's see. Let's make sure that, Carrie didn't make a mistake here. If we graph a 235 degree angle, this is 180 of those degrees. So we do 235 minus 180. That leaves us with 55 degrees. So this little angle in here, the reference angle, is 55 degrees short. Let me use a different color. 55 degrees short of the, or past the 180 degree mark. If we look at the same thing with 125 gets us here. If we want to get all the way to 180, let's see, 125 plus 55, that does give us 180, so that also is off by 55. So this one is the correct answer. They end in the same place, this orange angle and this green negative angle. All right, determine the value of each of the following. What is that? All right, well, we learned that these are called, in general, reciprocal trig functions. So the word reciprocal basically means a flipped fraction. So if you think about our regular trig functions, so, ka, toa, these are all fractions, right? We can flip all of them. So when sine gets flipped, sine becomes cosecant. And cosecant of theta is equal to the flip of this, hypotenuse over opposite. Cosine also has an opposite, and weirdly, the S1 here becomes the C. The C1 here becomes an S, which stands for secant theta. Secant theta is going to be hypotenuse over adjacent. And then finally, tangent is the easiest one to remember because when you flip tangent, it becomes cotangent theta. And that is the flip of this, adjacent divided by opposite. All right, so here we go. Cosecant of 45 degrees. That sounds tricky still, but then we remember we've got our 45, 45, 90 triangle. That's not how a 45, 45, 90 triangle looks. It should be isosceles because these are both the same size, 45, 45, and 90. 1, 1, root 2. So here we go. If we started with this 45 degree angle, we could label these opposite, hypotenuse, adjacent. Sine is going to be, cosecant is going to be hypotenuse divided by opposite. So square root of 2 over 1, better known as just square root of 2. Because when you divide something by 1, it's just itself. Cotangent 30. All right, 30, 60, 90. Always putting the 30 degree angle here. Let's see, 1, 2, square root of 3. Cotangent is, let's label these. We're looking at 30, so here we go. Opposite, hypotenuse, adjacent. So cotangent is going to be adjacent over opposite. So square root of 3 over 1. Square root of 3 divided by 1 is just square root of 3 if you fully simplify it. Secant 60 is going to be the same triangle. 30, 60, 90. 30, 60, 90. 1, 2, square root of 3. But this time, we're focusing in on 60. So this becomes opposite. Notice that this was opposite, now this is, because we changed our focus angle. This is the adjacent, this is the hypotenuse. Secant 60 is going to be, secant is down here. Hypotenuse over adjacent, hypotenuse over adjacent. 2 over 1, which is just 2. Cool. All right, reciprocal trig functions, all done. What did we learn about next? All right, we learned that this idea of a triangle is pretty useful. It got us pretty far. We did all this cool stuff. We did all this cool stuff with triangles, but sometimes when you graph an angle, it ends up in the coordinate plane. And this is particularly useful for angles like this one that would be too big to fit in a right triangle. So this allows us to find the sine, cosine, and tangent of these new angles. An angle theta is graphed in standard position. The terminal side passes through the point 15, 8. Which of the following trigonometric ratios is correct? All right, here we go. All right, well, this one actually you could figure it out in general because it's in the first quadrant. But if this is theta here, the terminal side passes through the point 15, 8. Let's see. All right, this distance is going to be 15 because that's 15 on the x-axis. This is 8 here, so that's going to be 8 here, which means if we wanted to figure out the r value, the radius out to this point, we could use the Pythagorean theorem because this is a right triangle. So we're going to do a squared plus b squared equals c squared, 15 squared plus 8 squared equals c squared, 225 plus 49 is equal, not 49, 64 is equal to c squared. And then we get 289 is equal to c squared. Square root both sides, c equals 17, so r is 17. All right. Now the key part of this problem is we had SOHCAHTOA, but we had our coordinate plane formulas as well. That's not them. Sine was y over r, cosine was x over r, and tangent was y over x. So sine is y over r. Is this y? Is this r? Yeah, that's y, but nope, that's not r. That's out. 15 over 8. Is this x? Because it says x here and r here. X is 15, R is not 8, R is 17, this guy's out. Sine is 8 over 17. Hey, all right, sine should be Y over R. We got it. Awesome. So you might be wondering, sometimes these are negative when we are in the coordinate plane. How come all of these are positive? Well, if you remember, all students take calculus, all of our trig functions should be positive in the first quadrant. So it is correct that we have positive 8 over 17. But for the next one, this might be different. Theta is an angle in the fourth quadrant, such that the tangent of theta is equal to negative 3 over 4. All right, so it's in the fourth quadrant. So we're going to take our angle, starting on the positive x-axis, opening it to the fourth quadrant. Okay, got it. We want cosine theta, so we think our coordinate plane formulas. Cosine is going to be that one, but we start off with tangent, so let's label these. We've got y, we've got x, using this definition. So let's see. Oh man, it's a negative fraction, first of all. So we have to decide, is the y value the one that was negative or the x value? Well, because we're going down, our y value is negative and our x value is positive. So we're at the point 4, negative 3 for our x and y coordinates. Next up, because we want cosine, we need to know our r value. So let's change colors and let's find our r value. This is a right triangle, so we need to use the Pythagorean theorem. A squared plus b squared equals c squared. If we plug in 4 for a, now the length of this side is 3, even though it's down 3. So when we plug it into the formula, we get 3 squared equals c squared. 16 plus 9 equals c squared. 25 equals c squared. Square root, c equals 5. So the radius out to that point is 5. All right, let's do a final check here. All students take calculus. Cosine should be positive because it's in the C quadrant. So we immediately eliminate these negative values here and here. And then cosine is supposed to be x over r, leaving us with this one here. Theta is an angle graphed in standard position. If the measure of theta is 5 pi over 3, then which of the following formulas gives the value of sine theta as a fraction? All right, so clearly we've moved on to part 2, second half of the unit, because theta is being measured in radians. All right, so let's make a graph. 5 pi over 3, I've got no idea where that is on the graph. But the good news is, it can be relatively simple to convert from radians to degrees, as long as we remember that a full circle is 2 pi radians. So if we wanted to know what pi radians is, that would be, well, that's half of this. So we'd have to do half of this. That would give us 180 degrees. This pi right here, if we converted pi radians to degrees, that's actually 180 degrees. Doing the calculations here, you can plug it all in Desmos, or you can just do it, and you get 300 degrees. Graphing that angle starts here. 300 degrees is going to be between 270 and 360, thinking about our key values. All right, well, how do we find a 300 degree angle? How do we find the sine of that? Well, one thing we know is all students take calculus, so only cosine should be positive. That means that sine is negative. This one's out. All right. So we're still a little stuck to find the particular numbers. But then we remember that when SOHCAHTOA fails, when the coordinate plane formulas fail, the reference angle is super helpful. Now the reference angle is always a positive acute angle whose terminal side, sorry, that's not correct, a positive acute angle which is between the terminal side, okay, terminal side, this guy, and the x-axis, this one here. All right, it's got to be acute, so that means he's got to be this little green angle right here, because that's the only one that fits this description, so that's alpha. All right, well, the red angle was 300. If we combine the red angle and the green angle, that has to make a full circle, because pictorially this and this is a full circle. So that's got to mean that alpha is the extra 60 degrees that when you combine with 300 gives you 360. All right, alpha is 60 degrees. How does that help us? Well, we remember that sine of theta is actually almost the same thing as sine of alpha. The reference angle and theta are very related. They have the same numbers, but sometimes have different signs. All right, so if we wanted to find the sine of theta, a much easier problem could be find the sine of 60 degrees. Sine 60, wow, okay, that should remind us back to here where we had our 30, 60, 90 triangles. So we draw our reference triangle. 30, 60, 90, 30, 60, 90. 1, 2, square root of 3. Sine of 60 is going to be opposite over hypotenuse. Square root of 3 over 2. So sine of theta is 5 pi over 3. Sine of 5 pi over 3, plugging that in for theta, has to be this. And if you wrote that, you're so close, but you lost a point because only cosine is positive in this quadrant, which means that sine is negative. So we get our answer choice. That was a big one. All right. So now, once we understood all there was to understand about angles in the coordinate plane, we moved on to looking at trig waves. So determine the equation of the function graphed below. All right, wow. So trig waves, it's hard to even remember how they connected, right? But we looked at graphing the values on a circle, and we saw that for sine, those values started to repeat, starting off at the midline. So instead of graphing many periods, for these, what we find useful is we find it really useful to keep track of what one period of sine looks like and one period of cosine. So sine starts at the midline, goes up, comes down, goes home. Cosine starts at the maximum, goes down, further down, back to the midline, back to the top, and then it repeats. And so you can see how that shape would repeat if we continued the wave. So we don't worry about that, because repeating is redundant with what we already did. All right, so here we go. This one's very sneaky, because they don't give us one period. They actually give us, let's see, 1, 2, 3 periods. So if 3 periods, 3 cycles equals 12 pi, then one period would have to give us 4 pi. So notice that value appears nowhere on our graph. But because 3 of them make 12 pi, one of them has to make 4 pi. And let's check it. 4 pi, that would mean 2 would be 4 pi plus 4 pi because it's the same cycle length, 8 pi. And then 4 pi plus 4 pi plus 4 pi, 8 pi plus 4 pi. That's, hey, 12 pi. That works. All right, let's put it all together. We've got y equals, starting at the midline, so sine of x. Is there a vertical shift? No, the midline is still in the same place, so we don't need a vertical shift. We do need to adjust the amplitude. The size of the oscillations from the midline are 5 units up, 5 units down, so that's a 5. And based on the period, we can calculate the b value that goes here. So set bx equal to 2 pi. But this isn't quite true. We're not really setting bx equal to 2 pi. What we're saying is at x equals 4 pi, we know that bx has to be one full period. Sorry, it looks like I'm dividing here. This is just emphasized. At x equals 4 pi, b of x equals 2 pi. All right, so we plug in 4 pi here. We divide by 4 pi on both sides, and that gives us b equals 2 divided by 4. is pi over 2, because you can reduce each of these by 2. Oh, nope, but the pi's cancel out. I got that wrong. It's not pi over 2. It's 1 over 2, because the pi's canceled out, and then we get 2 over 4. All right, so the last step is to plug that into our formula here, which gives us 1/2. All right. Determine the equation of the trig function graph below. It doesn't even look like a trig function. What are they doing here? I think they're giving us like the top half, but it's really stretched out because it's like 3 pi. So if we know it's a trig function, it's probably going to continue down, and then it's going to go back to wherever it started so that it can repeat. If half of it is 3 pi, that means a full version of it would have to be twice that, 6 pi, because you've got the up half and the down half. All right, so we get y equals 2, because the amplitude is 2, sine, because it starts off at the midline, bx, because b is hard to figure out, no vertical shift. To find b, we say at x equals 6 pi, bx has to equal 1 full cycle, because you go all the way up, all the way down, back home. So bx has to equal 2 pi, 1 full circle, 1 full cycle. So we plug this in for x, b times 6 pi equals 2 pi. We divide by 6 pi on both sides. We get b is equal to 2 over 6, can be reduced by 2. b is equal to 1. 2 divided by 2 is 1. 6 divided by 2 is 3. 1/3. So y equals 2. That's really sloppy. Y equals 2 sine 1/3 x. All right, last one here. The amount of blood in someone's heart can be modeled using a sine function. Cool, we already did that today. If the volume of blood varies between 20 milliliters, okay, having a picture is helpful here. 20 milliliters and 80 milliliters. Okay. Midline is going to be, well, that's not midline, because midline should be in the middle. Okay, well, what's in the middle of 20 and 80? It's a bit tricky to figure out, but you can average these together. 20 plus 80, and then divided by 2, we'll find the exact midpoint between those, because the average. 20 plus 80 is 100 divided by 2. This is us finding the midline. So cool. 50 right here. Let's check if that works. If this is going to be the maximum and this is going to be the minimum. This is up 30. This is down 30. That works. So we graph our sine function. All right. Well, what's the only thing missing? I didn't read the rest of the problem. Someone's heart beats 120 times per minute after running. If your heart beats 120 times per minute, then you have to inflate, deflate, back to normal. 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 120 times per minute. So we're going to complete 120 times per minute. But we don't want to know how long 120 of these things take. 120 of them take a minute. We want to know what's the period, so how long does a single one of these take? So if you take your minute, we can fit 120 of these inside of it, because our heart beats 120 times per the minute. So each one of these, the period is going to be, well, if you can fit 120 of them in a minute, you have to take that minute and divide it into 120 pieces. So the period is going to be 1/120th of a minute. All right, so putting it all together, let's get our equation. V of t, or V equals whatever it is, the volume of blood as a function of time is amplitude. Okay, from 50 to 80, we saw that that was 30. The amplitude is 30. Sine function. B is a little tricky to figure out, so we'll come back to that in a second. T is t, time. And then the midline is at 50 this time, so we have to add 50. To calculate the B value, what we say is at t equals 1/120 at one period, b of t has to equal 1 full cycle, 2 pi, because you go through the full sine cycle. So plugging this in, we get b times 1 over 120 equals 2 pi. And the last step is to solve for b. We multiply by 120 on both sides. That cancels out our division here. B times 1 is just b. 120 times 2 pi is 240 pi. So b is 240 pi. And it looks like we've got our final answer. All right, guys. So that was our whole unit. And it's remarkable the scope of the trig unit. By starting off with triangles, and if you're not sure like really where some of this pieces came from after watching this review, you always have those lessons available where we derive these key results, so you can re-watch those. But the progression here is unbelievable. You start with a triangle, you end up in the coordinate plane because you want to do angles that don't fit in triangles. You find some new formulas that work and are equivalent to the old formulas. And then based on those formulas, you're able to figure out that when you graph a sine function, it makes a wave, and that allows you to model anything that repeats: a heartbeat, an electrical impulse, the daylight hours over time, the tides of the ocean, actually a wave in the ocean, a guitar string. All of those, because they repeat or they oscillate in time or space, can be modeled with sine or cosine functions using math. All right, this is where we end this chapter, guys. If you want to continue studying sine and cosine functions, you'll talk about them a lot in calculus. But you'll also, if you continue taking it, take a class probably called partial differential equations or differential equations. And you'll learn how to further model sound waves and things like that using these. All right, guys, this has been a great unit. Good luck on the test and Delta Math.